Alright, today's video we're going to take a look at how we're going to calculate volume, which would be an appropriate kind of segue from where we were in section 7.1, which was calculating area. So the next application of our definite integrals is going to be that we're going to be calculating volumes. Now, just as area is always positive, you do want to recall that volume is also going to always be a positive number. So the whole idea where we were doing area with top minus bottom and calculating our heights were always positive, our widths were always positive, so area is always positive. The same thing is true for volume. Volume is always positive. And just like we did in the area unit, we are going to go back and we're going to start the volume unit by reviewing volumes of known solids, of things that you know from geometry. So we're basically going back to known geometric formulas that we're going to ground our idea of how we're going to find volume by looking at how we would have found volume when you took your geometry classes earlier. And the big idea is that to calculate volume of a three-dimensional figure, you are always going to calculate the area of your base, and this is specifically for a geometric prism, and then you are going to multiply it times the height of the prism, and that if you have those two things involved, then you are always going to be able to calculate the volume. It's always area of the base of the prism times the height of the prism. All right. And so obviously if we just look at some very well-known geometric formulas, that when you look here at your volume of a rectangular box, your length and width right here, that is nothing more than the area of your rectangular base times your height. So it was the area of the base of the prism, which is down here, length times width, times your height. If we look at a circular prism like we have over here, notice that the first component, pi r squared right here, that is the area of your circular base. And then of course times the height, and that would give us our volume that we're looking at. If we think of this in terms of dimensional analysis, we're taking a area which is in square units, and then we're multiplying that times your height, which is just in whatever the units were, and square units times units would give us cubic units. And so that's how we're going to get our volume. Now, and it doesn't really matter if the base that you have, it does not necessarily need to be a known geometric figure, because we've learned in section 7.1 that even if you have an irregular shaped base, that you need to find the area of the region, that I can find this area using our techniques from 7.1 if I needed to. And so I could calculate the volume by first calculating the area using our 7.1 information, and remembering things like top minus bottom and right minus left, depending on which way the area is situated, and then multiply times the height to get the volume. All right. Now, one of the things that you want to think of here is that not everything comes in nice rectangular prisms that we're going to be able to find volume. Just like not everything comes in known areas, known regions that are circles or squares or triangles when we're doing area. That sometimes we have irregular shaped regions for area. We also have irregularly shaped three-dimensional objects that we are going to need to find the volume for. Now, and the idea here is very similar to what we did when we were finding area of an irregular region, that we were using Riemann sums in order to calculate the area of a region. And what we had done when we were doing area is our area, if you will recall, we summed up the rectangles. We turned every region and sliced it into rectangles, and we basically summed it up, and we took each rectangle, we summed it up, the area of each rectangle. To find the area of each rectangle, we had the height of the rectangle times the width of the rectangle, and we took the limit as n goes to infinity, and that found the area and turned it into a Riemann sum. And what that also learned in that chapter is that this Riemann sum is nothing more than a definite integral of our f of x dx, that was how we were going to find our irregular shaped region's area. So we're going to use a very similar idea to find the volume of this figure right here. We have an irregular shaped, kind of amorphous looking figure, and what we did up here is we turned the irregular shape into rectangles. We sliced it into rectangles. Now think about this like slicing a loaf of bread. We are going to slice this, and when we slice this, we're actually going to be slicing it into basically regular geometric prisms. And that's the idea that we're going to do. Here we sliced into rectangles, and then we did the area of each rectangle, and then we added them up. Here what we're going to do volume, we're still going to be doing a limit as n goes to infinity. We're still going to be adding up all the volumes, okay? And the volumes that I'm going to be adding up, we're going to develop that, is going to be the volume of each slice. And each slice is going to be a regular geometric prism that we're going to have known geometric formulas to help us find that out. And then we remember, how do we calculate the volume of each regular geometric prism? We find the area of the base, and because we're doing this slicing it vertically, a little bit of review, it's going to have a function of x, just like this was a function of x, and then we're going to have our delta x, our width of each one. So we're going to do exactly the same thing we did before. Now notice, in terms of units, if we sum the areas, unit times unit, you get unit squared. If I sum the volumes, I have square units times units, which is giving me units cubed, so I'm ending up with my volume that we're going to take a look at. All right, so and kind of taking a look at this idea, here is my picture where I am slicing, and when I slice, I get this irregular kind of shape that I have, but this part right here, I'm just going to highlight this so that we can kind of specifically look at this one representative slice of bread that we have. That if I were to look at this, no matter how I slice, because of the way that our width is coming across, and then let's kind of get out this other side over here, that this right here is a regular geometric prism. The height is going to be the delta x, and then the area of the base, this portion right here, I'll highlight it here in green, this right here is going to be considered to be the base. I know you're kind of thinking base should be down here, but this is going to be the base of the prism that we are going to find the volume by taking the area times the height. So this is going to be considered the height of the prism, and then this is going to be the base of the prism. So we're going to take the area of the base times the height, and that'll give us the area of one slice. And then what we do with this slice is we're then going to sum them up. Here's our formula for finding the area. So this is area of this little green section over here, okay? And you take your area times your height. So this is your base area times your height of the prism. And that will give you the volume of one prism. But remember, we have several of these, and we're going to add up these prisms. And you can see that this volume that we add up is an approximation of the volume because, of course, you know, rectangles only approximated the area. The prisms are only going to approximate the volume. Now what we can do to make them better and better approximations, we're going to slice the regions thinner and thinner. We're going to basically let n, the number of slices that we take go to infinity, and our delta x, when we do that, is going to go to 0, and we're going to get better approximations of our volume. So it's nothing more than a Riemann sum. So we are finding a definition of volume by looking at a Riemann sum. All right, so the formula that we're going to look at, and this is when we're slicing them, where we are slicing perpendicular to the x-axis, just like we're doing above, that when I slice perpendicular, I'm slicing vertical slices, that we know that the width of the prism, or basically the height of the prism, is going to be delta x. So there's your height of your prism. Then this a of x sub I is representing the area of the base of the prism. We then multiply those two, and remember this is finding the volume of that one prism. We add up all the volumes. We can take the limit as delta x goes to 0, or an alternative way to write this, which is what we had done, we would take the limit as n goes to infinity, the sum I equals 1 to n of this a sub xi times delta x. And that if you get this Riemann sum and add it up, just like before, this will become a definite integral. Now, the difference between what we had before and what we are currently looking at is that when we did area as a Riemann sum, it was the definite integral a to b of f of x dx, that we had height times width of the rectangle, which is what was summing up the areas. Here I have area times height, which is three-dimensional and is summing up the volumes. And so that's kind of the idea of how we're going to calculate our volumes. Now let's kind of show you an example by looking at finding the volume of a sphere. Okay. Now the way that this usually works is this is what we call a solid of revolution. And so the idea is that what we're going to do is we're going to first think about this in 2 dimensions. So instead of going directly to my little sphere over here that I have already sliced into some approximations, I am going to start the problem by simply thinking about what would be the 2D version of a sphere. The 2D version of a sphere would be a circle. So we're going to have a circle right here. It's going to have a radius r. All right, and now let's think about this in 2 dimensions. In 2 dimensions, we have x and we have y. We do know a relationship. We have a formula for this curve. It's not a function, but that's okay. We know that the formula is going to be x squared plus y squared equals r squared. Now what we're going to do, and this is why this is called a solid of revolution, what we're going to do is we're going to actually take this 2-dimensional figure and we're going to rotate it around the x-axis. So we're going to kind of spin this around the x-axis, and it's going to turn it into a sphere. All right, and so if we do this rotation, you kind of have to visualize a little bit with me that we're going to spin this circle around. I couldn't find an animation to show you. But we're basically going to take this curve and we're going to spin it around, and it's going to create a 3-dimensional figure when we do that. Now, to kind of show that I have 3 dimensions, usually what you do is you draw in kind of a great circle like you would have a diameter of your sphere to show that we've spun this around. And you'll just have to visualize that we took this top and we flipped it back around and came back around to this side until it fills in and creates a solid sphere. This is why it's called a solid of revolution. Now, what we want to remember when we're looking at this then is that our objective, which I imported this little picture over here, is that we want this solid that we're looking at, we're going to slice it. So I'm just going to import this because I want to be able to kind of show you the different slices that you have. Now if you'd like to know where I got that picture from, this is called a Wolfram demonstration. So pretty much if you just search on Wolfram's Alpha's website, or demonstrations.wolfram.com. You can find a couple of these things, and what this was is it just allowed me to have a sphere, and it's showing you us slicing it into Riemann sums, like kind of showing you can rotate it around and see that if you look at it directly, you would have this kind of visual representation where you only see the rectangles. But because we're in the three-dimensional world, that each time we slice, we get what is essentially a disk, and the disk has a circular base, which is a known area that we're going to be able to find. And then what we're going to need to find for each disk is the radius of the disk, because obviously the radius of the disk is not the same as the radius of the sphere that you're looking at. That the radius of the disk, I'll bring this over here just so we can take a look at it, that the radius of each disk is going to depend on what point I am on the original curve that you had. So I'm basically going back to the 2D part and recognizing that this point xy is in the 2D world. And so I do know a relationship between x and y and the radius of the sphere by using this formula up here. Okay, this was the curve that I originally started with that I rotated around. All right, so now if we take a look at that prism that we have created, I'm just going to pull one out as a representative prism, that if I could find the volume of one of these prisms, then I'm going to be able to calculate the volume by adding it up and doing a Riemann sum. Well, the width or the height of this prism we're going to do as delta x, or also known as dx. And then we're going to talk about our area of this prism's base, which happens to be circular, and we're going to need this area as a function of x in order to do this problem. And because we are going to be summing up the areas, we're going to be doing the Riemann sum or using the definite integral. So now let's talk about this area as a function of x. What we know is that this area can be found by doing pi r squared. Now we have to be careful here, and this r is the radius of the sphere. This r is going to be a function of x, and it is going to be dependent upon where I am slicing it. That obviously if I slice it here, the x that corresponds to this one is going to have a different radius than if I slice it here for this x, then the radius would be up to there. So this is r as a function of x, so my area, which would be pi r squared, would be this capital R of x is what I'll call this, to differentiate it from the little r, which was the sphere's radius. So the area of the base is going to be pi times r as a function of x squared. Now, what do we put in there? How do we find that radius? Hopefully you'll notice that this radius is being drawn exactly to the point on the two-dimensional curve that we had started with to rotate of xy. So if I pick the x here on our curve, then I know what my height is going to be by looking at the y value, so the y is my r of x, as long as I know y as a function of x. And the question is, well, can I get y as a function of x? The answer is yes. I can solve, and the nice thing here is this is where my r of x is. So r of x squared is this y squared. So you're matching that up, so r of x squared is going to end up in this problem being x squared, r squared minus x squared. All right, so that's our area formula, where we have found our area formula as a function of x. Don't let this little r bother you. This is a constant in this problem. So it is a constant minus x squared, so area is now a function of x. So our Riemann sum then, if we wanted to find the volume of the sphere, we could sum up all of the prisms starting from negative r to r, because that's a constant, the bounds on x, right? Our width is in x, our area is a function of x, our bounds our x values, just like we were talking before when we did it with the area in 7.1, and it goes from negative r to r for our bounds, of our area formula, a of x dx, which is going to be my negative r to r. My a of x is going to be this pi r squared minus x squared, and then dx. Now, we basically just need to integrate that. When we're integrating that, remember that r squared is a constant. Now, I'm also going to make one change here, mostly because it's easier when you're doing your fundamental theorem of calculus with net change. This is symmetric, right? So we could basically do twice the integral from 0 to r of pi r squared minus x squared dx. That would be easier to plug in 0. And this pi is a constant, and I'm going to pull that all the way out to the front. So it's 2 pi definite integral 0 to r of r squared minus x squared dx. Now remember, this r is a constant. So I need the antiderivative. Let's bring our 2 pi here. I need the antiderivative of a constant, which would be the constant times the difference in your bounds, minus, now I need the antiderivative of x squared, so that would be 1/3 x cubed, and we're evaluating this last term from our 0 to r. So that's me just doing our calculations. So we have 2 pi, this becomes r cubed, I'm going to go ahead and multiply through while I'm here, minus 2 pi times, now I plug in my r, 1/3 r cubed minus 0. We end up with 2 pi r cubed minus 2 pi over 3 r cubed, which is nothing more than combining like terms. That's 6 pi over 3 minus 2 pi over 3, 4 pi or 4/3 pi r cubed, which is how we know is our known formula for volume of a sphere that we just proved it. So kind of recapping what I did here, okay, just to make sure that we're kind of clear on the process, is I took a two-dimensional figure, and the two-dimensional figure was the circle. So I had the circle in 2 dimensions. Okay. I took the equation of the circle to get a relationship to tell me kind of where things were. I then spun the circle around the x-axis, rotated it to make a solid of revolution, which is a sphere. And then as the sphere gets sliced, I sliced it vertically, so I have dx. And to find the area of each prism, I took the area of the base times dx. I added them up, turned it into a Riemann sum, which is a definite integral, and then used that to calculate the volume of the sphere. And that's exactly what we're going to do for pretty much this one class of problems. These are called solids of revolution. And the nice thing about solids of rotation or solids of revolution, that every time you do a solid of rotation, your cross-sectional base of your geometric prism is always going to be a circle. And that's the key to this. So we know that when we find the area as a function of x, that area of that prism is always going to be pi times whatever the radius is of that circle as a function of x squared. And then to calculate our volume, remember that what we do is we do the sum of the area times dx. So pi r squared dx is the volume of each prism that we sliced, of each slice. The slices are always going to be disks, and to find the volume, you add up all the disks, the volume of each disk. Now, kind of, yes, this is not a word, but we are going to start using this because it's going to help us remember what we're doing. when you slice, when you do a solid of rotation, you will always rotate around an axis. This axis is either going to be horizontal, as it was in the case that we're kind of doing. We're taking the x-axis as our axis of rotation, and we rotate around that. And when we rotate around that, you always create basically an irregular shaped figure, but the prism that we're slicing it into, each slice will always be a nice disc. And we always slice perpendicular to the axis of rotation, always. And when we do this one right now, the axis of rotation is horizontal. We sliced vertically here. And when we slice vertically, the thing that you want to remember here, and this is the thing to keep in track, is that your area is going to be a function of x, your width is going to be dx, and your bounds are going to be x values. Okay? Now, the difference between, now this, and this is pi r squared dx, this r of x, let's put it over here on our figure so that we have it, is this radius right here. This is the radius of the disk that we get from each slice. That radius is a function of x because it depends on where I slice it vertically. Now we are also going to do this same problem, but instead of slicing it with an axis of rotation that's horizontal, we could also be doing this where we have an axis of rotation that is vertical. I'll just kind of show that one over on this side. So if this is now my axis of rotation, and we're going to spin it around this way, then every time we get a disc or a slice, our slices are now going to be horizontal. And this should start being like ding, 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 things that we did in section 7.1. We are still going to find the volume by taking area of the base times the height. But now the difference is when you slice this way, and you see how it's perpendicular, vertical, axis of rotation, horizontal, disk, our width or height of the disk is going to be dy. We are now going to need to find the radius as a function of y. So our area of the base is going to be a function of y. It's going to be pi times r of y squared. So in this case, when we do this situation, our volume is going to be pi integral a to b of r of y squared dy, and actually because I want to emphasize that this is all in terms of y, and my bounds are y values. So this, we'll usually do c to d when I do the y values. So those are going to be the two volume formulas for a solid of rotation or solid of revolution. Okay? And your job is to decide which way are you slicing, and you always slice perpendicular to your axis that you're rotating around. Okay? Now I'm going to stop this video here and make this an introduction. And then what we'll do is we'll pick up and we'll just basically do the setup and kind of go through the examples to show you how the examples are going to work. So for my students in AP classes, this is kind of about where I had gotten to in a Friday class, and so I will stop there and then we'll pick up and we'll do the examples for this to kind of show how this works.